AWS Identity and Access Management, commonly known as IAM, operates as a foundational, global, and entirely region-agnostic security engine. Because it exists outside of any specific geographical boundary, every identity and permission configuration you create propagates simultaneously across the entire AWS ecosystem. This creates a singular, centralized directory for resource control. When you first provision an AWS environment, you start with the root account. This entity holds unrestricted superuser privileges over every resource in the environment. From a strict architectural standpoint, you must never use this account for daily operations. Instead, your immediate priority is locking it down by linking a physical multi-factor authentication device. With an MFA device bound to the account, a physical security key becomes the primary barrier against unauthorized root access, even if the password itself is compromised. Once secured, the root account serves a single narrow purpose: initializing your primary administrative identities to operate below that threshold. A secure cloud architecture requires you to abandon that root credential immediately and rely entirely on a scalable, delegated identity model. These delegated digital identities are known as IAM users, representing the direct mapping of physical human operators or automated systemic workloads into AWS. To manage these operators efficiently at scale, we use IAM Groups. Groups establish logical boundaries, allowing you to collect multiple users and apply security permissions to all of them at once. However, there is a strict structural rule. IAM Groups cannot contain other groups under any circumstances. Instead of nesting groups, individual users act as highly modular components. A single IAM user can belong to multiple distinct groups simultaneously, inheriting the combined permissions of each. Conversely, a user is not required to belong to any group at all. They can exist as a standalone entity with their own directly attached policies. Enforcing this flat, non-hierarchical structure prevents permission bloat and ensures that during an audit, a user's exact access level remains mathematically predictable. To actually grant or deny those access levels, AWS relies on JSON policies. This is the exact computational language that binds specific permissions to your entities. Writing these authorization policies requires defining strict parameters within a JSON document. Every valid policy contains two mandatory top-level fields: a version date, which must explicitly be set to 2012-10-17 to match the policy language release, and a statement block. Inside that statement block, we find the 6 pillars of control: an optional SID identifier, the effect dictating an allow or deny, the target principal, the specific API action, the exact AWS resource, and an optional condition block. Defining the resource pillar requires extreme precision. You must target resources using their exact Amazon resource names, or ARNs. For example, in Amazon S3, a bucket-level ARN to list contents looks like S3::test. But object-level ARNs required to actually read or write files demand a wildcard suffix, like S3::test/*. Mastering this strict JSON syntax and precise ARN targeting is the non-negotiable prerequisite for implementing a true least privilege architecture. Even with perfectly scoped JSON policies, the environment remains vulnerable if the login perimeter is weak. Strict password policies and multi-factor authentication act as your foundational lines of defense. You secure console access by enforcing standard variables, high alphanumeric complexity, strict rotation limits, and hardware locks preventing password reuse. But securing the perimeter is only the first step. You must also rely on programmatic auditing to verify that your granular policies are actually effective in practice. At the macro level, the IAM Credentials Report provides an account-wide audit of all active access keys and password ages. At the micro level, the IAM Access Advisor provides user-level telemetry, tracking exactly which AWS services an identity has used and precisely when they last called them. Together, these tools generate the empirical telemetry required to confidently strip away unused permissions over time. When workloads scale, static users are often insufficient. For dynamic, temporary credential delegation, we use IAM roles. Rules are governed by the rule assumption rule. When an entity assumes a role, it completely surrenders its original permissions in exchange for the temporary credentials of that new role. This contrasts sharply with resource-based policies. When a policy is attached directly to a resource, like an S3 bucket, the calling principal retains all of their original identity-based permissions while interacting with it. Choosing between dynamic roles and static resource policies dictates the exact permission state of the principal during an operation. As infrastructure scales to an enterprise level, managing individual accounts becomes untenable. AWS Organizations allows you to cluster multi-account environments into organizational units, or OUs. To govern these massive structures, we apply service control policies, or SCPs. These act as enterprise guardrails that establish the absolute maximum allowable permissions for any account within an OU. There is one architectural exception to this rule. The organization's management account is entirely immune to SCP restrictions. For all other accounts, SCPs enforce the final law of IAM. An explicit deny in any policy layer unconditionally overrides any explicit allow. This chart maps the policy evaluation logic AWS uses. The engine processes a complex flowchart to reach a final decision. When an API call routes through SCPs, resource policies, and identity policies, hitting an explicit deny at any stage terminates evaluation immediately, overriding any allows. A secure enterprise architecture requires balancing these unyielding organizational guardrails at the top with precise, dynamic access controls deployed at the edge.